All right, so today I would like to talk about circuits which contain a resistor, capacitor, and inductor, and not necessarily all three simultaneously. So I like to show now what will happen if we connect resistor, capacitor, and an inductor in series and connect it to a source of sinusoidal alternating current. So let's figure out how the current depends on the parameters of the elements. So let's say that we know what is capacitance of the capacitor, what is the inductance of the inductor, resistance of the resistor, and let's assume that we have an ideal source of sinusoidal alternating current. I mark current flowing clockwise on this diagram. And well, in order to have this current to be equal to the rate at which the capacitor is being charged, I would have, consistently, if I mark current that way, then I should put Q on the left-hand side. So current I should flow toward the plate which has charge Q in order to have a relationship between current and charge, that this current is equal to the derivative of charge on the capacitor, time derivative of the charge on the capacitor. All right, so why don't we use loop rule and write an equation which relates current to that electromotive force. And rather than thinking about the differential equation, because if I, in general, if I do not use phasors and complex analysis, I would have to use differential equation. Actually, this equation would be valid also for real analysis. So voltage, I wrote here that the potential difference between this point and this point is equal to potential difference between this point and this point, which is potential difference across the resistor, plus potential difference between this point and this point, which means potential difference across the inductor, plus potential difference between this point and this point, which is potential difference across the capacitor. I really use loop rule. In principle, I would have plus on this side and minus on this side. So I could write down that 0 equals to the sum of potential difference across all four elements, and because this is given, I move it to the other side. All right. Now, if it were real analysis, actually, why don't we write the equation? If I have a pen, yes, I do. If I use real voltages, I could write down that potential difference produced by the source of electromotive force is equal to potential difference across the resistor plus potential difference across the inductor plus potential difference across the capacitor. Now, just to make sure, what are these? Could you tell me what's VR? Correct. This is I said that it is potential difference across the resistor. However, I didn't specify which one. So, which one? No. It's across the resistor, but which potential difference across the resistor do I have over there? Actually, for the other ones, it isn't even true. For which one it is true? Well, you don't, because now you have forgotten actually what this could mean. You are thinking like it was constant currents, constant current. Now, if we refer to potential difference or potential for an alternating current, we can have, well, at least three concepts in mind. What are they? Peak voltage, for example, Yes, so is it peak voltage? No. What else could I have in mind? A what? Root mean square value voltage. Is this root mean square values? Is it for root mean square values? No. Okay. What's the third one? Instantaneous. Correct. So over here, all three functions of time and only for for instantaneous. This is true. Now, how about these ones? Is it complex? Is it instantaneous or complex amplitude? Andrew?
So it's instantaneous. Thinking back to our definition
of the phasors, yes. Think about the phasors. Actually, it's for both. It's for complex amplitude. This one is true for complex amplitudes, and this one is true also for instantaneous. All right. Now, let's start with this one, and so that we see advantage of considering phasors and complex analysis. Let's now write down or relate potential difference across the resistor with current. What should I write consistently with the drawing? Yes, so consistently with the drawing, I want now to write potential difference between this point and this point. Potential difference across the resistor is related to this current. How? Directly, correct. So it's proportional to current. What's the proportionality coefficient? What? Resistance of the resistor, correct. Should I put plus now or minus? Because both are directly. Should I put plus or minus? Who votes for plus? Who votes for minus? Plus is correct. All right. Next, let's relate potential across the actor through the inductor. How related? Yes. Potential diff is proportional to the rate of change in current. I have to diff of, and this is rate. What's the probability coefficient? Inductance of the correct. It should, if I arrow there, it would the right. So of rate of in the gives me potential. This is what to add potential difference across the capacitor and related to current. To do it right away. So what do I have to do? Well, from the fact that it is a capacitor, well, why don't we? Because potential difference across the capacitor is directly related to the charge, and this charge happens to be related to that current. So first let's express it in terms of charge and then convert it to current. So let's write down in terms of charge. How potential difference is related across the capacitor is related to charge. Charge divided by capacitance, correct. So here we have charge divided by capacitance. Should I put plus or minus? Plus again. All right, we got such an equation. Well, let's convert everything to current because now we have too many variables. So what should I do that I get rid of that charge? Well, I can calculate the derivative of both sides. Right? So if I calculate the derivative of both sides, I will have derivative of the electromotive force, and I will order now them neatly. So here I have already derivative. So if I calculate derivative of derivative, I will get second derivative of current. Here I will have first derivative of current. And here I will have 1 over c times derivative of charge, which will give me current. So I got an equation now which allows me to find current. Yeah, so now we just we can just solve this differential equation and get current. Well, this is what we would get if we, and actually we could do it in a relatively easy way because we know that it's a sinusoidal current. And on top of it, electromotive force is also a sinusoidal function. So I can plug in a general form for the current. That current is equal to peak current times sine of angular frequency times time plus delta I. And I also can write down that electromotive force is peak value of the electromotive force times sine of omega t plus, and I will put initial phase of the voltage. So I can plug in those values, and from that I can find out, relate peak value of the current to peak value of that voltage, and also relate the phases. Now let's see what will happen if I use complex analysis, because complex analysis already performing or calculating derivative is equivalent to multiplication. We have to multiply a complex function by something in order to get the derivative. All right. So in result, actually, complex potential difference across an element is equal to complex impedance of this element multiplied by complex current for all three elements. Oh, I'm drawing the phasor now. So let's say that here I have the phasor representing this current. And actually, yeah, I mean, this will be a good interpretation, I mean, comprehension of this, what we have over there. All right, so let's now draw phasors corresponding to each of the three voltages. So how should I draw the phasor corresponding to the voltage across the resistor? Which way it is going to be and how long? Adam is right. Phasor corresponding to voltage across the resistor is going to be in the same direction as phasor for the current. How long that phasor should be then? Well, it depends on the resistance. If resistance is 1, the two phasors would be equal. If resistance is 2, phasor of the voltage should be 2 times longer. If resistance is 10 kilo ohms, then phasor for voltage across the resistor should be 10,000 times longer. So I would advise to change this, to use a different scale for voltage and for current. All right, good. Now let's draw the phasor corresponding to voltage across the inductor. How should I mark that one? Well, how long it is going to be depends on impedance of the inductor. So let's start with this assumption that impedance of the inductor is 1 ohm. Impedance of the inductor is 1 ohm, which means that how long should be the phasor corresponding to voltage across the inductor? Same as I, correct. Now, if impedance of the inductor were 10 kilo ohms, how long should be the phasor representing the voltage? Of the chart, 10,000 times longer. We can change the scale and make it 10 times longer, for example. All right, now how about the direction of the phasor? Here recall that phasor actually relates also simultaneously peak values and phases. And in an inductor, what leads what, and depending on that, we will have appropriately to draw the phasor. Kyle, do you remember what leads what in an inductor?
Well, I know that the phase of the inductor is 90 degrees ahead of the.
Yes, a phase angle of an inductor is 90 degrees. All right, which means that what leads what? I tell you actually what my teacher in high school once said. I mean, it's a silly story, but allows me always to remember I mean, so this is not science. It's just a story. Which I actually don't promote. I mean, you noticed probably on the test that a lot of you didn't get credit for half a page of writing because I wrote that it's a story. All right, but here is the story. He said that, well, since potential differences are measured between the points, well, so if you take an inductor, voltage travels along straight line. And an inductor current, because inductor is made from a coil, current has to go through all the loops. So it has longer way, therefore it is later than the voltage. So this is just a silly story which allows you to remember what leads what. In capacitor it's the other way. So if you remember how it is in the inductor, then you will remember how it is in capacitor. So what leads what in an inductor then? Voltage leads current. Okay, so how the phasors will be related? Definitely phasor for the voltage across the inductor will be at 90 degrees to the phasor of the current. But which way? In which quadrant? Which one? Yeah, current is behind. Yeah, 90 degrees to this current, it will be either either second quadrant or fourth quadrant. Which one? Second. Correct. Voltage across the inductor, phasor representing voltage across the inductor is going to be in the second quadrant. Now let's go to the phasor across the capacitor. It's this time voltage lags behind the current by 90 degrees, so this one is going to be in the fourth. All right, so these three complex numbers, this one, and this one, represent voltage across the resistor, inductor, and capacitor. Now we have to add these three complex numbers in order to get phasor, this phasor. Okay, so this phasor now is equal to the sum of those three. Yeah, and when we add complex numbers, we add real parts separately from imaginary parts. So adding phasors really is the same as adding vectors. Actually, this is why it is called phase vector. So if I add those three green vectors, I will get the phasor which corresponds to the voltage across the entire circuit. And well, I could write it in the form of, I mean, using complex numbers. Voltage across the resistor is, complex voltage across the resistor is complex current through the resistor multiplied by impedance of the resistor. Complex voltage across the inductor is equal to complex current through the inductor times impedance of the inductor. Complex impedance of the inductor, I omega L is complex impedance of the inductor. And complex voltage across the capacitor is equal to complex current across the capacitor multiplied by complex impedance of the capacitor is minus I over omega C. All right. Now let's find how the peak value of the voltage and peak value of the current are related. We can do it. We can do it over here. What would we have to compare on the phasor diagram in order to relate peak values? How long the phasors are, correct. We will have to compare the lengths of the phasors. So let's say that this one has length IM. How long is this one? Well, on the drawing. How about if you try to calculate that? Just looking at the geometrical interpretation. All right, so if we start at the length of phasor representing current is Im. So it's length of phasor representing the current. So how long is the phasor representing? Well, let's start with the voltage across the resistor. In other words, how long, what is VRM? How is this one related to the peak value of the current?
Looks like 1.5.
I'm not asking, yeah, it looks 1.5, but why 1.5? Yes, Andrew, why is it 1.5? Resistance times peak value of the current. And why did we multiply by resistance? Why do I multiply by resistance? Because in principle I should not multiply by resistance but by something else. By what? The peak value of the voltage across the resistor is equal to peak value of the current across the resistor multiplied by what of the resistor?
Resistivity.
Not resistivity. I mean, resistors don't have resistivity. What?
The complex of them.
Not complex. What relates, and actually, I mean, I think that last week we were relating these. What were equal and what were not equal. Impedance, correct. Impedance, yeah, peak value of the voltage is equal to peak value of the current multiplied by impedance of the resistor. But coincidence, impedance of the resistor is equal to its resistance, so I have resistance. All right, now how long is the phasor representing voltage across the inductor? How this one is related to peak value of the current. Owen. We have to multiply by, again, peak value of the voltage across the inductor is equal to peak value of the current across through the inductor multiplied by impedance of the inductor, correct. And impedance of an inductor is related directly to the inductance of the inductor. How? I mean, in principle, I could even write, yeah, let's write it down here. Let's get rid of this R here, and I will put impedance of the resistor. Here is impedance of the inductor. Now, how peak value of the voltage across the capacitor is related to peak value of the current? How? By, what should I put here? Z sub C, which stands for impedance of the capacitor. All right. So we expressed now length of this phasor to the length of the current phasor, length of this phasor to the length of the current phasor, and length of this phasor to the length of the current phasor. How long is this one then? Now look that it forms, this is a hypotenuse of a right triangle like that. Do you see this? Do you see a right triangle over here? All right. So this length, the length of there's a peak value of the voltage. Now, this is length of hypotenuse. So from the Pythagorean theorem, I can write down that this is square root. And what do I need over there? Not current squared, but I need this one. Right? Correct. Peak value of the O across the resistance resistor squared plus what? Difference between the other two, right? Length of the other two. Correct. As I will write down. Peak value of the potential difference across the inductor minus peak value of the potential difference across the capacitor and squared. All right. Now I will explicitly relate it to the peak value of the current. So this one will give me square of impedance across the resistor times peak value of the current squared plus this one will give me impedance of the inductor times peak value of the current minus impedance of the capacitor times peak value of the current squared. I can take out this, I have peak value of the current everywhere, squared, right? Because over here I can pull it out, right? And I will have ZL minus ZC. And I will have to square it. I can take it completely outside of the square root. And here I will have square of impedance of the resistor plus difference of impedances squared. How about if I go back now to the top and write it down here? What is impedance? Let's relate impedance of resistor, inductor, and capacitor with the most commonly given parameters characterizing these elements. So usually when we go to the electronic shop, we don't ask a resistor of certain impedance, we ask for a resistor with a certain resistance. So how impedance is related to resistance? They are equal, correct. So here I have square of resistance plus impedance of the inductor. If you go to a shop, you will ask an inductor with a particular inductance because impedance happens to be a function of angular frequency. So what is impedance of the inductor at angular frequency omega? Omega L. How about impedance of a capacitor? Again, if you go, it is a function of angular frequency. If we go to electronic shop, they will sell a capacitor with a particular capacitance. So it is 1 over omega C and squared. All right. Now, how would I find it from this expression? Yeah, because now, here I have complex voltage across the circuit. This is current flowing through the circuit multiplied by this number. What does this number represent, therefore? Not voltage. No, voltage is here. It's complex voltage. Complex voltage is related to complex current by a coefficient called what do we call this coefficient, which relates complex? All right, yeah, what is it? Complex impedance, correct. So we can recognize that this expression over here is the complex impedance. How do we find impedance then? We take absolute value of complex impedance and we get impedance. Look at that now. Are we happy? Why? It's the same thing as we see over there, right? Do you see now what is the mechanism, how the phases really work? Now, how about if we find the phase angle? Where should I look on the phasor diagram for the phase angle? Where is it? Between the red and blue line. The angle between the red and blue line is the phase angle. By the way, phase angle, I mean on this diagram, phase angle is positive or negative? Negative. And how do you know that? Because the phasor of the voltage is behind the phasor of the current. Remember that those, as time passes by, what do these phasors do? They all rotate counterclockwise, and always phasor of the current is ahead of phasor of the voltage. All right, how do we find phase angle directly from complex impedance? Andrew, do you remember that? Tangent of the phase angle is equal to imaginary part of complex impedance divided by real part of complex impedance. Now, what is imaginary part of complex impedance over here? Can you identify that? Omega, or whatever is after the I. Yes, so this is imaginary part of complex impedance. I have it here. And real part is the resistance. And actually, over here, I could also recognize that. Yeah, because if I take what I have to do, tangent of this angle is equal to this length divided by this length. Do you see that? Yeah, now, how long is this segment over here? Christy has already indicated, told us. Christy, how long is that? It was the difference between those two phasors, and if we pulled out I from everything, we will just have difference in impedance of the inductor and capacitor. And now how long will be this one? It will have Im times a peak value of the current multiplied by resistance. All right. Why don't we talk about resonance tomorrow? So we just covered one slide today, but that's fine.